Everybody okay? So we will continue today also with the quiz. So everybody keep their pen and paper ready. And hopefully we'll have a winner at the end of the talk. So I've rearranged my talk a little bit since you know, we had such a wonderful 2 talks about deep learning, and I just wanted to sort of give you an alternative. So deep learning, it's questionable at this point whether it's really appropriate and applicable to medical image analysis. And the reason is that, you know, we have, instead of 2D images, we now have 3D volumes, huge numbers of voxels, and the data sets are not like 15 million images that you can sort of get from the web, but more like a couple of hundred images, or if you're lucky, a couple of thousand images. Right? So it's not so clear that convolutional neural nets at this point will work really well for you know, for the medical imaging domain. So actually, when we started, you know, we started to try deep convolutional neural nets on 3D MRI images of Alzheimer's patients, and actually it didn't work all that well. So we tried, and you know, you get into horrible overfitting, and so anyway, so it's either waiting for more data or for better methods to regularize these methods. In the end, I think you know, they will win out. In the end, I think, you know, we will all be doing convolutional neural nets, but for now it seems quite hard. So as an alternative, there is something else which I think you should be aware of, which seems to be working actually quite well, and this is what's called a scattering transform. So this is a technique by Joan Brunat and Stéphane Malat, and what they did was basically said, well, let's think about how a neural network actually works. I mean, what does it do? And then just hard code that into some architecture and not learn anything. Just treat it as a transformation on your data. So you could alternatively think of this as what's been talked about before. You train a neural net like on a huge image database, which is unrelated to your task, let's say ordinary images. And then you use that fixed architecture to then produce features for another task. And I think this has been somewhat successful also in the medical imaging domain. But this scattering transform, basically what it does, so it has 2 types of filters. It has a simple Gaussian filter, which is a blurring filter, which we call phi. And there's another wavelet filter, which I'll show you here. So these are the types of wavelet filters. It's quite standard, like a Bohr type wavelet filters. And this is our filter phi here. And we have this sort of wavelet filter in different orientations and in different scales, basically. And so basically what they have theoretical arguments for is to say, well, a deep neural net basically does the following set of transforms. So you start with your image, and the first thing, so that's a bit different from a convnet where you actually only look at the last layer. But they spit out first a blurred version of your input image. And then they convolve the input image with a wavelet at every possible scale and every possible orientation. So you could make 8 orientations and 4 scales or something like that. They take the absolute value of that, and then they blur again. Right? And then they output these images as well. And they also downsample, so the images become smaller as well. So you see, you know, you got the pooling operation, which is making them smaller. You got the nonlinearity, which is taking the absolute value here. And you get the convolution with some kind of, you know, preset filter here as well, which is this object. And then, and again, the difference is that you output those coefficients. And you keep going. And then for every one of the filters that you produced, filter outputs that you produced, after taking the absolute value, you'll then do it again for every possible, you know, orientation and every possible scale, right? And output those. So now the number of coefficients is starting to explode. But you downsample again, just like in the convnet, and you output all of those numbers. So if you keep on doing that, you get a whole lot of numbers in the end, right? Actually, all these black things. And those are the things that you then train an SVM on, a classifier on. So now note that you haven't trained anything here. So there's no worry of overfitting. You just have mapped your data into a new space. That's all you did. But of course, after this, you would have to train on the coefficients that you're getting. You have to then train an SVM, right? And the SVM, has parameters, so that could overfit. Okay, so here is what you would get. So here's your input image, which is sort of an MRI scan, one slice of an MRI scan. I wonder if it would help if we would close those windows. I'm not sure if that would help for the images, but. So this is the output of layer 0, which is basically a blurred version of itself. And then actually you sum over all of this. I don't think you have to do that. You could, you could keep some of the spatial information if you wanted to, and sort of, average over these and average over here and average over here and there, or you could even take every pixel value. But what we did and what this was recommended is you average basically this image. And then at the next level, it's much harder to see here. So now for different orientations and different scales, you then again do your convolutions and you do your magnitude, and then you get these images, which are now smaller, but now have gradient information at different scales and different orientations. And you keep going. So here it's very hard to see now, but so again, you then take every one of those and you convolve them with every filter at every orientation and scale, and you produce these images. And then again, you average all of these. So you keep on doing that, and that will give you a whole bunch of numbers, like 10,000 numbers or something. And based on that, you'll train a classifier. Okay, so this is also hard to see. But what we did is we trained those on really small data sets. So these are data sets with maybe between 100 and 150 images, right? And we tried, these are ROC curves. There's a number of data sets. There's an HRV data set. So basically looking at how does the brain change for an HIV patient, right? How will that brain, they sometimes get cognitive impairment because of that disease. And it's unfortunately very hard to see, but I'll trace it out. So these are two standard methods, which is directly using an SVM or using ICA, which is independent component analysis, and then as an SVM classifier on those. You'll see the ROC curves here, and then the green curve goes here. Well, you have to believe me that it sort of nicely sort of gets up. So this one is not so much better. It's a little bit better. It's OASIS data set. This one is quite a bit better. ADNI, HC versus AD. No, anyway, so all of these sort of show a little bit of improvement, which shows sort of that this process is somewhat viable at least. And then we did maybe a more challenging experiment where we found that these guys had state of the art, which was trying to classify progressive MCI, mild cognitive impairment versus stable MCI. So I guess these people actually develop Alzheimer and these stay in the MCI phase. And then, so again, we used scattering plus an SVM. We got to 73, where the state of the art was 69. And then if we did scattering plus Laplacian SVM, which actually is a semi-supervised learning method, where you actually use some unlabeled data as well, we got it to 82%, which I think at this point is state of the art. But, ADNI is cut in many different ways, and so sometimes it's not so easy to compare to other methods. So here's some visualizations of the result, and as you might expect, I'm not a neuroscientist, but I think what I've been told is that what you see nicely is that these regions here around the hippocampus light up, and so for the people that are in the PMCI group, you would actually expect that the hippocampus is the region that is affected, and for the stable ones, what you would see is, in fact, that the hippocampus is not lighting up as much, but it's more like a global change, more like here and here. And I'm thinking maybe that is just ordinary shrinkage of the brain. Maybe we did regress out age, so this is maybe brains that age a bit faster than normal brains. Okay, so that was that, a little bit of deep learning. So I also wanted to show a little bit of how you visualize deep learning. So this is a method that we developed. So the idea is that, so here actually, Maybe these results actually come from Andrea's paper. I'm not sure. This is the saliency maps. Maybe you recognize them. I'm not sure whether they come from your paper or not, but so this is if you have sort of a penguin image, you're trying to find those pixels which are responsible for a particular decision, right? So if you say that which pixels are actually responsible for classifying this image in the king penguin class, and you find that it sort of finds, for the different architectures, VGG, GoogleNet, and AlexNet, you find that it of course focuses on the penguin. So what we did something completely different. We said, well, let's look at the log odds of the class. Log odds is basically this object, the probability of assigning an image X to class C divided by 1 minus the probability of assigning image X to class C. So for class C, if the probability is high, this thing gets close to 1, or gets infinity. And then, and so the log odds is a measure of how much evidence there is for assigning that particular image to class C. And then what we did is we looked at the difference between that assignment with every pixel in and the assignment with some pixels left out. So we basically said, well, if we leave some pixels out, how much does it affect that assignment to that class? And if the change is large, then those pixels must have been very important for making that particular classification happen. And so, well, there's one little trick that we have to play here, which is we have to compute this thing efficiently. And one thing you could do is you just black it out, so make it white, black, basically. But of course, black is also something, right? And so that's not really the way you want to do it. You want to actually average them out or marginalize them out. And the way to do that is to say, well, what is this P of C given X without pixel I or group I? Well, using Bayes' rule, you can say it's the probability of C given, everything, and then times the probability of Xi given X not I, and then integrate over Xi. So that's, so this is just using Bayes' rule on this. So this here is equivalent to this. And then you integrate out Xi. So then the question is, how do you integrate out Xi? Well, we have a little model for this one, which is basically, we have a little model for this guy here, which is you look at a pixel and you look at the surrounding pixels, and then you have a simple Gaussian model to predict the value of that Xi given its surround. So you can compute this very quickly, and this is your ordinary classifier that you just have. So you compute this reasonably efficient, and then what you see is quite nice. So you see that there is positive evidence, which is here in red. So the positive evidence is always on this region of the penguin because it's very distinctive, right? So it thinks that these are the most sort of distinctive pixels in order to put that particular image in this class. And then, here around the head, it actually finds negative evidence. So it's saying, well, this region around the head is actually, working against this assignment. And I think the reason is that there's many other penguins or birds in this data set. And so that maybe this head is actually more like another penguin's head if in this particular photograph. So this actually votes for another class, right? But most of the votes coming from the body actually come for the correct class, and therefore it puts it in the correct class. Okay, so now you could imagine, and we actually have done this, doing this for medical images. So if you have a classifier in the medical imaging domain, then sort of this will very nicely tell you which part of the CT scan or the MRI scan was responsible for predicting that this is an Alzheimer patient, or whether maybe even working against predicting again, for another class, maybe healthy patients. And this could be very useful, of course, in the clinic. Now I'll say a few words about this. This goes back to Andrea's talk. We've worked on sort of, can you train models where if you build in this equivariance? So if you have this equivariance where you know that if your image is, say, rotating under a particular angle, right, you want, and so if you know that, you want to enforce that in the higher layers, there's also some transformation that you can understand on the latent or the sort of the deep representation of the neural net. I'm not going to go into the details. There's another paper by DeepMind which does something similar. I just want to say that this idea, if you bake it in, and it's quite simple because it's one of those boxes that you see in these architecture. So you just take out the normal convolutional box and you stick in this particular rotation equivariant convolutional box, and you'll just see, and it's not much more expensive. And what you see is that the performance is getting much better. So it's really sort of a module that you can swap out and give you much better performance. Okay, so here is a particular piece of work I just want to highlight a little bit, which has to do with, let's say if you have some kind of architecture and you know, for instance, that a part of your images were taken in hospital 1 and another part of your images were taken in hospital 2. And so they were acquired with different MRI machines, right? And you already know that, so let's say maybe one was an academic hospital and very sick patients were sent to the academic hospital, and the other one was sort of a more regional hospital, and sort of the not so sick patients were actually scanned in that hospital. So then the hospital ID is immediately starting to correlate with the possible outcome of a treatment, for instance, right? Or maybe the diagnosis. And so really you don't want that sort of hospital ID information in your representation. But the problem is that since the scanners are different, right, one might be a bit more blurred than the other one, you'll start to regress on things like, okay, if my image is more blurred, then the outcome is going to be much better for you, right? Because you happen to be sort of scanned in a hospital where less sick patients were. So you want to remove that information. So again, I won't really talk about the details. There's a paper you can read. It's very similar to domain adaptation. So in domain adaptation, you have maybe observations in 2 different domains. You've trained a classifier in one domain, and now you want to test it in another domain. And so how can you make sure that it still works? So you can look at this image. You can see this is face images. It's very hard to see, unfortunately. But so these are face images. And it's a 2-dimensional sort of a manifold representation of those images. And these are faces taken under different lighting conditions, right? So if your task is to sort of classify a particular face or to detect a particular face, then you can already see from here that the dominant signal is actually the lighting condition, right? And so you want to remove that lighting condition, and using this particular technique, you now see if you make a new mapping, a manifold sort of mapping of the images, you'll see now that this lighting condition is not the driving signal for clustering this data. So another thing I wanted to briefly sort of highlight is that in deep learning, we also often want uncertainties. And actually, the current deep neural nets are very poor at producing correct confidence intervals. So if you're in a self-driving car, it's far better to have an algorithm that would have a slightly less high accuracy, a slightly lower accuracy, but that is very good at telling you that it doesn't understand the scene that it's currently seeing, right? And then it would say, I give you back the steering wheel, just I don't know what I'm doing, so just you grab the steering wheel. Where in the other case, you would very confidently drive into a tree, for instance. And then also for doctors, I think this is quite similar. If you have a system and you started to trust it, you really want to know, how certain is this algorithm of making a prediction? So if you want to prescribe chemotherapy, then clearly this is very, hard on the patient. So you would only want to do that when you're very certain of your diagnosis. And if you're not so certain of the diagnosis, you want to do more tests. So we've been working on Bayesian neural networks, which basically put these uncertainty intervals around these predictions. Okay, so here's a first quiz question then. It's quiz 6, but I'll be going back in a minute to slides that come before, since I've reordered a little bit. So the question is, scattering transforms are not learned from data and can as such not overfit. But a classifier trained on these scattering coefficients can therefore also not overfit. right? So both have to be correct for you to answer either, for you to answer A. So the question is the real question is if you train an SVM classifier on top of a scattering transform, can you still overfit? All right, so let's see A. Who says A? True, so this is true. Okay, so the answer is B, because because you're fitting something in the second level, you can actually still overfit quite easily, right? Because, in fact, these scattering transforms can give you a huge number of coefficients, and if you do a linear, even though the SVM is linear, there's still the possibility of overfit on that linear, on that large in a high-dimensional space. Okay. Oops. So now I'll go back to where I left off last time, which are the variational autoencoders. So this is work I did with Dirk Kingma, and the idea is that we really wanted to marry the discriminative deep neural nets with generative models, because as I've argued, so the generative models you can think of as sort of the graphical models view of the world, like a Bayes net. You start with some interpretable latent variables, and you imagine how you can generate the data from those interpretable latent variables. Or you can think of that as a simulator. So here I can here's the first sort of example. So think of this as, so you have some disease label that you sometimes observe. So some patients, you know what their disease is, what the condition is when they come in, and they're in your data set, let's say Alzheimer. You know the hospital ID, and there's some latent variables that you haven't quite yet identified yet, so they're unobserved, right? But these could become things like, the size of the hippocampus, or even the sort of a little bit of the orientation of the scan, etc. So all of these together then sort of go through a complicated sort of transformation, which basically you can think of as a deep neural network in the generative direction. And they produce an image. Now, this is actually quite challenging to produce a good image, but you can imagine that something like that, could happen from sort of some deep neural network. In fact, I think the better way to think about this is this, which is a simulation of some kind. I mean, this could be a simulation of maybe a heart, or a simulation of a brain, right? So instead of having this deep neural net, maybe you have just a very large piece of computer code, maybe some partial differential equations or something like that, that would actually produce realistic sort of images or realistic scenarios like this, right? This is actually really cool, but wait a minute, because these are two galaxies that collide, and this is a true simulation. And at some point, so no star will hit any other star, but this is what happens when you have two galaxies collide. All right, so boom, beautiful. Okay, so in fact, there's a field now which which bridges between, let's say, this thing of a Bayesian net, a graphical model, and a simulator, which we call probabilistic programming. So probabilistic programming is a field where you basically have a computer language in which you can sort of program things, but stochastically and probabilistically, and you can produce these kinds of things. Okay, so that's the generative lag. So let me maybe go back to this image. So this is the generative lag. So from some latent variables, you go to some observed sort of image maybe. And then there is a discriminative lag. So this you should think of as your traditional sort of deep neural network that tries to discriminate things. So here, the image goes in, and maybe something like the hospital ID, everything that you have observed goes in. And then there's some deep neural network structure that then needs to do two things. So the first thing it needs to do is to produce the posterior distribution of that Z. Now, if you think back of what we did yesterday, right, we had this generalized, or this variational EM algorithm, right? And in the variational EM algorithm, we needed to approximate the posterior of all our latent variables z given x. Right? I'll go into more detail in a minute. So that's what this network is going to produce. And I already alluded to the fact that you can actually sort of get one of these qz given x by basically using a deep neural net. So the first thing it needs to do is to produce the posterior distribution over z given x. And then in some other way, you also want to produce the label y. So the y, the label could be directly generated from x, which would just be really an ordinary neural net, or you could choose to say predict the label y from the label representation z that you get here. So maybe base the prediction more on the semantic sort of space of things that are happening. So maybe these things could actually be very meaningful in terms of the images that you see. Okay, so now we have two legs. We have a generative version of a model. We have a generative model and we have a discriminative model. And if we go back to our discussion, both have advantages, right? So these could be extremely flexible and therefore have their advantages. But here you can put in your prior knowledge, your expert knowledge. And so I just want to show this then again. So if you look at this, physicists have thought for centuries about how the laws of physics work, right? I mean, this is basically general relativity at work here. And so it's just silly to throw all that information away and to just try to learn that from just observing the sky, right? So here, all that knowledge that physicists have acquired over centuries is encoded in this probabilistic program, right, in this simulator. And there's still a lot of free parameters, like, what is the angle at which, these galaxies collide, or how big was the galaxy, or how fast did it rotate, or something like that, right? And you could try to then actually observe things in the sky and then sort of fit this simulation to the actual data that you see in the sky, right? But the important thing is that you can encode all your information that you have as an expert in this generative model. Okay, so I just want to give a little bit of background on this idea that you have a generative model and a discriminative model. So we were not the first to think of this. So there is this paper. Everything seems to point back to Jeff Hinton in some way or other. So here's another one that goes back to Jeff Hinton and his collaborators, Peter DeHaan, Hinton Frey, Neil Zemmel. And that's the paper that they call the Helmholtz machine. So the Helmholtz machine, this is a picture from their paper. There's the green lines, which represent P of x given z. And then there's the red lines, which is what they call the recognition network, which tries to infer the P of z given x. So it's going the other way back. Okay? And they had an algorithm which they called the wake-sleep algorithm to train this. Right? And in the wake-sleep algorithm, it's quite similar to EM, but it's not EM actually. There's not a single objective that's being optimized. And so in the wake phase, basically what you do is you condition on your data x, right? It's like you're awake, so you're looking at the world, and so there's data coming in. So you're conditioned on the data x, and you're sampling samples for your latent variables here from your distribution Q that you currently have. Okay, and then you do an update. So now you have samples for both x and z, where x is the data and z is from your model, and then you can compute a gradient update in order to improve your parameters of your generative model P. So you can sort of think of this as the M step in some. Well, you can think of this as the E step in some sense, and then you do an update. And then this is an M step, basically. And then there's also the sleep phase. And in the sleep phase, it's like you close your eyes, and you basically use your generative model to generate, images of the world, right? So it's like you dream. In your dream, you're not conditioning on any data. It's just basically stuff that's in your model, which is your brain. Right? And you draw first, from latent variable z, arbitrary latent variable z, and then given z, you draw, observations or pseudo-observations x. Right? So now both x and z are fake. They're both, at least here x was data, but here they're both fake. And then using those x and z's that you generated, you can actually now show that you can do an update on q. So now you're training q up, which is like the E phase of the EM algorithm. So it looks a lot like a variational EM algorithm, right? Where there's a q distribution, which does not necessarily have to be the true posterior distribution, but it's trying to approximate P of Z given X. And then there's a generative model P, and sort of there's two phases in which these things are optimized. But it turns out that actually this thing is not optimizing a single objective. So it's just basically two phases, and in the end, the whole thing might fluctuate a little bit. It doesn't really converge, and it didn't really work very well. So people sort of largely abandoned it, I think. So what we did is basically we went back to, well, why are we not treating this as an ordinary variational EM algorithm, right? So the key idea was to have this recognition network. So to have this network which goes from the input to the latent variables. One network that you can very quickly evaluate going from the data to the latent variables. And this could perfectly fit into a variational EM framework, right? And so basically what we said was, just, forget that, think of what I did yesterday. That's all the math you need for it, right? It's really just the variational EM algorithm. And then there's two updates. There's the standard M update, which is basically doing gradient descent on the parameters of your generative model P. And then you can also just compute the gradient of the variational distribution Q. You can just go ahead and compute that gradient, right? And it's one objective, single same objective. So and that, if you work it out, it looks like this. So it's the expected value over your distribution, your approximate posterior distribution Q of Z given X. And then you have to evaluate this function inside. So you have to evaluate the gradient of log Q. That's the log of P divided by Q here. Now the problem is, and now you could go ahead and say, well, I cannot actually compute that average. But one thing that I could do is just draw samples from this Q. So this Q is a neural net, so you can just evaluate it, very quickly from the data to the Z's, and you just generate some data Z. You can do this very quickly, and that's fine. But the problem is that if you try to do that, it turns out that the variance is going to be very, very high. And that's the reason that it didn't work. In fact, there's two reasons why the variance is high. One is because you're sampling from Q, but the other one is because you're also subsampling the data at every iteration. So there's two sampling procedures, and that those procedures basically generate noise. And so this means that your gradient, where there's one gradient, your gradient is all over the place with very high variance. And you're looking in the mist, right? You don't know where you have to go uphill. You don't know where uphill is on this cost function, because you cannot really estimate that gradient here very well. And I think that's the reason why, basically, I'm sure people tried this, but that's the reason, they found out that it didn't work for them. And so, we basically identified that the problem was that this variance, so the variance was the problem in the gradient. And so, then the question was, can you do something about it, right? And so Kingma so it had a very clever trick, which was what we call the reparameterization trick. And it's super simple. It's amazingly effective. And the idea is, so I'm writing out, again, this gradient here. It's the same equation that I had on the slide before. So it's the log of the generative model minus the log of the approximate posterior, and then averaged over this Q. And the trick is, what you're going to do is you're going to reparameterize this Q in the following way. So you're going to pull. What you really want to have here is a standard distribution, like a normal distribution, a standard distribution. And you can do that by transforming Z. So if you say, well, Z is some function of the parent and a random number epsilon in the parameter state, it's some deterministic function of that. Then you can say that epsilon is actually from, let's say, a standard distribution, maybe a normal distribution or something standard, right? So you say, okay, so I'm going to transform from Z to epsilon, where epsilon is drawn from some standard distribution, say normal standard distribution, and then Z is now some complicated function of the parents and the parameters and that random variable epsilon. So then if you do that, then this gradient does not depend on anything anymore, so you can just sample from these guys. And then the gradient looks like this. So it's the derivative of this difference. So now this term is gone, which is very important. And then z needs to be evaluated at epsilon and phi. So this derivative acts both here, but it also acts here and here, because now z is a function of phi. Okay, so this may be a bit sort of complicated, but you know, let me give you an example of how significant this can be. So if you try to compute the gradient of a random variable z with respect to a normal distribution with mean mu and sigma here, right? And then I compute the gradient with respect to mu, what should be the answer? Can somebody see the answer here? So if you evaluate this, right, what will come out? Does anybody see it if you raise your hand? Right, so if this is the mean, it has to be mu, right? Because this is a normal distribution with mean mu, and I'm trying to compute the mean, basically, of that thing. So that's mu. So taking the gradient with respect to mu is going to be 1. So the answer is 1. Okay? So we know what the answer is. Now, but if we are sort of naive, we can sort of draw samples from n. So draw some samples from this n here, and then stick them in. So we're going to draw them, oh, sorry, I'm basically going to do this trick here. So taking the gradient, moving it in, and following this procedure. And then if you do the estimation, you have something like this. Now, if you work it out, it's 1. So if you draw enough samples, you'll get 1. But for a finite sample set, this will give you highly fluctuating answers, because it's like this z times, one z times another z, and it's a multiplication of two things, and this thing goes all over the place. So it's very difficult, you need a lot of samples to see that this thing is actually 1. If you do the reparameterization trick where you say, well, let's reparameterize z as mu plus sigma times epsilon, where epsilon is now drawn from a standard normal distribution with mean 0 and standard deviation 1, right? Then if you do that, so here you have epsilon drawn from the standard distribution, then the answer is 1 over s, sum over s of 1. Now that's 1. Well, however many samples you draw, the answer to this is always 1. Right? So the variance after the reparameterization trick is 0, and here the variance is huge. So basically, this very, very simple trick will allow you, that's the bottom line, will allow you to compute those gradients that you need in the E step. And then things start to work really nicely for you. Okay, so here's sort of the setup that we have. So we have a distribution over Z, the latent variables. And then there's a neural network or a simulator or whatever you want that produces the parameters of some distribution P. It could be the mean and the variance or something like that. And then there is, you can draw from that distribution samples X. And the other one is the sort of the discriminative model, which is also a deep neural net that starts from X, again goes through a deep neural net, again produces a mean and a standard deviation, and then produces Q of Z given X. Okay, so now we have our two legs, and you can think of this leg here as computing, the approximate posterior for Z, right? So this is just in the variational EM interpretation. This guy needs this guy in order to compute the P of Z given X. But you can also think of this guy as trying to regularize this guy. So if you think of this actually, and that's going to be more clear in a minute when we actually also include labels. But you can sort of, this guy, if this is free, like a Q distribution, this guy is trying to constrain this to be its own posterior. Okay, so if you run this, it's again hard to see, but so what we do here, so this is faces. We trained it on a data set of faces. And then we just fly through latent space, Z space, and for every value of Z, we then draw an image. So that's our generative model. For every value of Z, which is a bunch of numbers, so you can think of this as the embeddings that Andrea and Raquel were talking about. Right, so this is just some vector of properties of a face, which could be like your skin color, the orientation, whether you wear glasses, whether you're a man or a woman, all of these kind of, these properties which make a face a face. And then you just randomly sample some value of z, and then you generate a face, right? And then this is the sort of the space of faces that you will encounter. So it's, you know, it does reasonably well, right? It can nicely generate these faces. But I think the more exciting application of all of this is actually when you start to include labels, right? So now, you know, we're in this scenario where we have a data set, and the data set sometimes has a label and sometimes not. So think of like MRI images, and some of the MRI images actually are labeled with this patient developed Alzheimer, but other MRI images are not labeled with anything. This is just some scan of some brain, okay? So that's what I mean with sort of a blob here, which is partly blue and partly green. Sometimes it's observed and sometimes not. So you can think of your generative model as, well, if you have the information about the label, you use it to generate, and then there's all these latent variables which have to do with the orientation and whatever, that are also instantiated, and then given those two, you then go through a neural net and generate your image of a brain, right? Okay, so that's your generative model, and you can put like your sophisticated knowledge about MRI, you know, images in here. So if you, this could be a sophisticated simulator that generates images of brains, basically. And then in this direction, what we have is an ordinary sort of neural net, which goes from your pixels. Let's say this could be a convolutional neural net that goes from the image and then goes through a whole lot of layers, blah, 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 and then it predicts the actual label. So it predicts whether this person is developing Alzheimer's or not, right? So this is an ordinary neural net, right? And then there's a second phase where we also need Z here. So we go from Y, you know, back and from X, and then we generate, again, through a deep net, also the posterior of Z, right? Now, if Y is observed, you can just, you know, include it here, right? And then this, you know, you don't have to use this leg, but you can use this leg, of course, to predict it afterwards, right? And then given this and this, you produce this. So if it's not observed, then given X, you first predict Y, and then using that prediction and X, you then predict Z. Okay, so you can do all those things. So now your objective changes a little bit because you have a part that has to deal with the data which have labels and a part that have to do with the data that have not labels, but it's not a very big change with respect to the, what we have for the variational EM. It's just another EM algorithm. But there's this extra term which actually was important, which is this is actually, you know, if you think that this, you're really interested in this prediction, you should give, you know, this particular thing a boost. You should say, I think this is really the most important thing, that I actually predict these labels correct. And so you're adding up a term here, which is basically, this is your predictor. This is just cross-entropy term with this is your convolutional neural net of Y given X, and then you have to average that over your data, over your observations. Right, so this is just giving a boost to the actual convnet that tries to predict the labels. And if you use those two, now you are in a semi-supervised learning framework, right? Because you use data, you use labeled data and unlabeled data to train up this particular network, which is making predictions. And the only reason why you can do that is you're modeling the input space, right? In the input space, if you know, we've seen a picture, I think, on the first day where, you know, if your data is clustered, right, then you want to use this sort of this clustering of the data to propagate the labels that you have inside these clusters, but not across sort of the low probability regions. Okay, so this is a semi-supervised learning setup now, so again, I want to emphasize that this, so you could directly train this guy here on the labeled data, but now this is there to support the semi-supervised learning. And it's also sort of regularizing this model a bit, right? Because this is saying, well, I really want you to be the inverse of me, right? And this is a generative model. So I want you to be the inverse of this generative direction. And this, you know, if we don't put this term here, it would need to do that. That would be the best solution. But with this extra term, it's saying, well, I also have some agenda of my own. I'm trying to really be good at prediction here, so I could sort of partially ignore the fact that I need to be the inverse of you. So this basically means that there is this, you can think of this generative model now as a regularizer for the predictor. I think that's very powerful because it's an informed regularizer rather than something like dropout or something. Well, we looked at some other architecture, so you can really plug and play. You know, you can put in some stochastic nodes at arbitrary positions. So these are just neural network deterministic layers, but you can put in some stochastic nodes at different layers, and you can plug and play. And we basically applied this to a semi-supervised learning method, where these are some other methods, and this is error, so you want to be low. And you see that especially when the number of labeled examples is very small, this method shines because it's modeling the input distribution. Now, I should also say that more recently there has been more development in this direction, and in particular the ladder networks, which is you can interpret actually as a variational autoencoder, but with these lateral connections. So the whole thing looks like a ladder, right? So you have two legs, right? But now instead of just going up and down, you now have also lateral connections between the up and the down. And I think Andrea actually showed something like that yesterday, where he was also transferring high resolution information, from one of the networks to the other, from the, discriminative network back to the sort of the convolutional network back to the deconvolutional network. So that's quite similar. And the ladder networks actually turn out to be even better at the semi-supervised learning task. So here's then something else fun that you can do. So it's not just good at making predictions and doing semi-supervised learning, but again, you can do this analogies. So where now we set the y variable to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that we just force it to be that, and then we fly through z-space, right? And if we again fly through z-space, then you see that z is actually predicting the style. It's modeling the style of the writing, right? And so you can see that you nicely capture the latent space dimensions, the relevant degrees of freedom that make up images and the way they're written. Okay, so I guess that's the variational autoencoder. So now we have another quiz. So training the variational autoencoder can be challenging because of the variance in the gradient with respect to the variational distribution Q. That's the first question. And the wake-sleep algorithm to train the Helmholtz machine is a version of the EM algorithm. And I've said these things actually almost literally, so if you've paid attention, then you can know. So the training of the variational autoencoder can be challenging because of the variance in the gradient with respect to the variational distribution Q. And the wake-sleep algorithm to train the Helmholtz machine is a version of an EM algorithm. Okay, so that's for the first one. Who thinks A is the right answer? Okay, that's correct. Who thinks B is the right answer? Okay, thank you for raising your hand. That's good. And then for this one, who thinks A is the right answer? The wake-sleep algorithm to train Helmholtz is a version of the EM. Who thinks A is the right answer? Who thinks B is the right answer? Right, so B is the right answer here because the wake-sleep algorithm, it does not optimize a single objective, right? It's two separate objectives. So now, who has answered all questions correctly so far? There's 1, 2, 3. In the back, do I miss somebody in the back? Okay, so am I correct? So let's raise again. So 1, 2, 3. I'm counting 3, 4. Did I miss anybody? Okay, so we're down to 4. Very good. This is halving, it's exponential. Okay, so how much time do I still have? I forgot. 20 minutes? Okay, so then the last part of the talk, I want to talk a bit about Markov chain Monte Carlo. So now we've talked mostly about variational inference. We've talked about deep learning and how deep learning can be combined with generative modeling, but that was all done within the variational EM framework. But there's another key technique to do inference, and Sandy was talking about this also a little bit in his talk, which is called Markov chain Monte Carlo, and abbreviated MCMC, which is also a very powerful technique. So this is sort of the idea. So if this is a distribution you're trying to approximate, you're now going, instead of actually coming up with some analytical solution, you're going to draw points, samples. And the samples will land somewhere here, but I want more samples in the position where the probability is high. Okay? And so you can see that if you draw a few samples, then it looks a bit noisy. And the more samples you're drawing, the more the histogram of your samples is going to approximate the true distribution. So that's if you're drawing correct samples. Okay, so let's first think a little bit about MCMC. Why do we actually need MCMC? I haven't explained MCMC yet, but I will in a minute. But MCMC is sort of a sequential procedure in which you draw samples. There's other ways you can draw samples, which is basically say, well, let's say that this here is where all the probability is in a two-dimensional space for the posterior distribution that I'm interested in. So again, let's imagine that we are Bayesian and that we're trying to figure out what the posterior distribution of our parameters given our data is, right? But it's very hard to compute it, and so we're now drawing samples. So let's say this is my true posterior distribution, so I can now draw from another distribution, let's say which is this one. I draw all these samples, and I basically reject everything that is in a very low probability region. And I keep only those that are inside the high probability region here. Right, now that's a procedure that is in theory correct. The only problem is that in high dimensions, this is exponentially inefficient, which basically means that the variance of your estimators are going to blow up, basically meaning that you never get it right. You never really hit the places where the probability is high. So it doesn't scale to high dimensions. Now, the solution to this is what's called Markov chain Monte Carlo, and that's really a very cunning, algorithm. It's very beautiful in many ways. And the idea is that you produce now a sequence of samples. So the next sample is going to be highly correlated with the previous sample. So let's say it's close to the previous sample, right? And so that these samples sort of evolve, and after a while, they move towards the actual distribution where the probability is high, and then they will start sampling from that distribution, right? So basically, you can think of it as you have a sample, and you perturb your previous sample, and then you evaluate whether the probability has gone up. And if it's gone up, you accept, and if it goes down, you think a bit harder. Okay, so here's a picture of it. So you start with your initial parameter value theta 0. It could be a random guess, right? And then we're trying to sample from this posterior distribution p theta given x, and we perturb our initial, sample, and let's say we accept it. So here's our next sample, and our next sample, and our next sample. And between two samples, we have this transition kernel, which is the probability of the next sample given the current sample. Right? So you can think of this as basically a Gaussian distribution centered around your current sample, and you're drawing a sample that's close by your current sample. And you keep on doing this, and then in the end, these samples are going to be cycling or moving around in the correct region of space where the probability of the target distribution is high. Okay, so the first bit, which is basically you can think of this as your optimization phase in some sense. It's called the burn-in phase, and these samples are not from the correct distribution, so you have to discard them, you have to throw them away. And then the final samples that are actually on the target are the ones that you need to keep. Okay, so there's a bunch of things that are good to compute. The first thing is, of course, when you have your samples and you have some function f that you want to compute an expectation over, so I want to compute the expected value of f given, over my distribution p, then I'm going to approximate this with this Monte Carlo sum. So we have seen this before, and there's two things which are important. The bias, which is asymptotically how well, if I draw an infinite number of samples, how well is this estimate of I, of this average, this is my estimate, how well is it going to approximate I, right? And for variational methods, this was non-zero, even if you would go on forever. But for sampling, the beauty is that it's actually 0. So if you sample long enough and you have a correct sampler, then in fact, you'll get the right answer in the end. That's very beautiful. But there is a catch, and the catch is that there is variance in this estimate. So if you sample for a finite time, let's say you draw 1,000 samples, right, you get some answer. And then you repeat the procedure and draw another 1,000 samples, you get another answer, right? And so the fluctuations of, for those 1,000 samples of how these answers vary, this is what we call the variance. And the variance goes down with the number of samples. So the more samples you draw, the better your estimate is going to be. But there's this thing which is called the autocorrelation time, which is how correlated are these samples that you're drawing. So how much is the next sample, how much does it depend on the previous sample? And if they depend a lot on each other, the variance in this estimator is going to go up, and that's a bad sign. So here you see an image of a sampler that's sampling over time, and here's the parameter that it's sampling. That is a high autocorrelation, right? So you see that it's changing, the samples are changing, but they're sort of changing in a sort of smooth trajectory almost, right? So the next sample really depends a lot on the previous sample. So that's not a very efficient sampler. Now this is much, much better because every next sample is almost independent of the previous sample. You can see no structure here. Okay, so then a little bit of background on sampling. So if I start with a distribution P0, let's say this is some initial distribution from which I draw my first sample. Okay, and now I have this transition kernel which says, which draws the next sample given the current sample. Right? Now you can do this for a sample, but you can also do this for the entire distribution. You can say, well, I have a probability over theta, and I'm going to convolve it with this transition kernel that produces a new distribution, P prime theta prime. So you can think you start with a little Gaussian, and then you draw a lot of samples from this Gaussian, and then given every sample, you draw a new sample. So given a sample, you draw a new sample from this conditional distribution. In the end, you'll get a new distribution, which may be slightly shifted, right, and maybe it's a bit expanded. Right, and that's my distribution P prime theta prime. I think I have a picture here maybe. Here, so here's a good picture. So here's my initial distribution P of theta, and here's my first sample, right? And then I apply this transition kernel, and here's P prime theta prime, right? So my distribution has shifted, and I'm drawing a new sample from this new distribution. So I keep going. So here's the new one, and this sort of moves towards the target distribution. And then I'm going to sample many samples from the target distribution. So that's how that works. But sort of this is the operation. It's very simple. It's a linear operation. So you have an initial P, you hit it with a transition kernel, you convolve it, and you get a new distribution. Now what you really want is that in the end, the P doesn't change anymore. Right? So here we had P prime, but you really want that P doesn't change anymore so that you have equilibrated, you have converged in this sampling sense. And the other thing you really want is that this P that you converge to is actually the target distribution. This should be your posterior distribution that you're interested in, right? So in other words, if we go back to the picture, so this distribution is moving, and then at some point it's not changing anymore. So that's when you've converged. And this distribution also needs to be the target distribution, the distribution that you're interested in. Okay, and now, so this is sort of your condition, and it's called the invariance condition. So it's the condition that says, you have a distribution, and I apply some transformation, and it doesn't change. It just stays exactly the same. But that's very hard to enforce. And there's another condition which we call detailed balance that is much, much easier to enforce. And that's basically saying, if I start with my target distribution and draw some sample from my target distribution, and then I apply the transition kernel, so I move, I try to change this distribution to a new distribution using my target here. Then that's exactly the same if I start at theta prime, which is the new sample that I was drawing, and apply the kernel again. So what this means is, you can see this in a picture. So what this means is, so here is a little bit of theta, right? So this is a little in theta space. And here's my probability in theta. So it says that if I'm thinking about moving mass around, probability mass around, so the probability of picking something out of this bucket and moving it here with my transition kernel, so this should be T, sorry, it should be T. has to be the same as the probability of picking something out of this bucket and moving it into this direction. So in other words, there's a flow of probability going in both directions, but the amount of probability in both directions has to be the same. Because if it's the same, then this distribution is not going to change. Right? Now clearly, because there's a higher probability of picking from this bucket, less has to move in this direction. So the kernel K has to move less in this direction than in this direction, since you multiply by the probability that you actually pick something out of that bucket. Okay, so I've shown this picture. So okay, now we have a procedure. So we have what's called the Metropolis-Hastings procedure that's going to try to use this detailed balance. So this detailed balance I claimed was easy to implement and enforce. And now we're going to develop an actual algorithm that will enforce this detailed balance. So again, I have a transition kernel T here, and what I'm going to do is see. Okay. So I have a proposal distribution. So this is a new object now. The proposal distribution is an arbitrary distribution that proposes a new sample given a current sample. So this could be like a Gaussian distribution around my current sample. I'm going to pick a new sample given my old sample. So this is what this Q does. And then the next is you're going to have to decide whether you're going to accept or reject that particular sample. So I've proposed a new sample. And basically the idea is if the probability at the new sample of the target distribution, P of theta, is higher, I'm always going to accept because I'm in a better place. But if it's lower, then I'm going to accept with a certain probability. And it's this probability that I'm going to accept with. So this is basically the probability of starting at theta t, at my current state, and going to theta prime, times the probability, so the probability of picking, the probability at my current sample times the probability of going from my current sample to my new sample, and that's in the denominator. And here is the reverse. So what happens if you go in the reverse direction? Probability of starting at my new sample and going backward to my current sample. And if you go uphill, then you can show that this is actually going up, and so you always accept, because this says the probability of accepting is the minimum of 1 and this, but this is going to go larger than 1, so you're going to accept its probability 1. But if this guy is actually a lot bigger than this guy, then you're going to accept only with a probability that is smaller than 1. Now, of course, P, this is the posterior distribution, so we know this. So fortunately, we don't need to compute the normalization constant because it cancels in these two expressions, so that's really convenient. So this is saying, is a new state more probable? This is saying, is it easy to come back to the current state? And then we compute this probability. Now, this looks great, and in fact, this is an algorithm that statisticians have been using for ages. There's many things you can improve about this, but there's also one thing which is bad about this, which is it does not pass the big data test, right? So remember yesterday, we talked about the big data test, and if your data set is infinitely large, right, will this actually run? Would it even do a single step? Right? And the answer is no, because in order to compute this, right, I have to do this. And this is a product, or in the log domain, it's a sum over n data points. So if my data set is infinitely large, then this is a computation which takes infinitely long, right? So this is a typical example of an algorithm that will not pass the big data test. And there's some other things that we won't discuss now. Okay, so what are we going? Can we do something about this, right? So that's the question now. And there's two methods that we can try to develop. So the first one is to say, well, maybe we can do this accept-reject test approximately. Maybe we can just say, well, let's not look at all the data in order to accept or reject the new sample, right? Or we can say, well, let's try to have some sort of proposal distribution that's so smart that I will always accept, and then make an approximation and say, well, let's evaluate this on a small number of data cases. Okay, so basically this is the picture that you should have in mind. You have a target distribution S0 that you want to sample from. Now you could develop some distribution, some sampling method which is actually not correct. So even asymptotically, if you draw an infinite number of samples, this will actually, not be correct. But you can draw a lot of samples because it's fast, right? So now you have bias, but you have very low variance. And then the other extreme, your sampling procedure is actually correct, but it takes a huge amount of time to draw even a single sample. And so given a limited amount of time, what you see is that you can only draw 3 samples, and so the variance is going to be very high. I'm wondering, how much time do I still have? 5 minutes? Okay, so I'll just skip over a few things. Right now, I just want to at least show you this here, because this is a really practical procedure that you could sort of apply and at least be approximately Bayesian. So if you would do, train a neural net or train anything at all, you would basically apply gradient descent, for instance. So you have the log, if you use a log sort of cross entropy as your loss function, then basically in order to compute the gradient of a parameter in your model, maybe this is a prior, so you could forget about it, but let's say you have some prior over your theta, and this is the usual term that you have, is the sum over all your data points of the log probability of those data points at the current parameter value, and you take the gradient. So that's just gradient descent. It's very simple. Now, nobody does gradient descent because it doesn't satisfy the big data test. So really what you want is a procedure that only draws a mini batch of samples and computes a gradient approximately on that mini batch. Right? So this is just stochastic gradient descent, which is instead of taking the sum over all the n data points, you take it over a small number of data points, and you compute the gradient, but then you rescale by n over n in order to make it at least at the same scale as your original gradient. Right? And there's some conditions that the step sizes need to satisfy. They need to go down in order to get to the correct answer. And the total sum has to be infinite, but the total sum squared has to be finite. And there's some schemes that you can follow. So that's standard. Everybody knows about it. And then we have Langevin dynamics. This is a very cunning procedure, in fact. This procedure is you just apply the same equation here, but you add noise. But the amount of noise you add to the gradient has a variance that is equal to the step size. So the variance is equal to the step size, actually the step size over 2. So the variance of the noise that you're adding is equal to the step size over 2. So they're coupled. And with this coupled set of equations, and epsilon very small, you will actually sample from the posterior distribution. It's like magic, but it's actually true. So it's like a dynamical equation. It's like doing gradient descent, but you add a bit of noise, and you're sampling from your posterior distribution. It's really nice. But basically what you can do is you can say, well, if we can do stochastic gradients, then maybe we can also do stochastic gradient Langevin dynamics. And it's literally the same. You take these gradients, you subsample them, you scale them back up with a factor, you add noise, the noise has certain conditions that it needs to satisfy, and then the whole thing basically is guaranteed, when epsilon goes to 0 slowly, is guaranteed to sample from the posterior distribution. So this satisfies the big data test clearly, because every update only depends on a small mini batch, and you're approximately sampling from the posterior distribution. So that's really nice. I had a demo here, unfortunately it doesn't work. Since we are running out of time, I'm going to skip over the rest. There's this other procedure, well, you can distribute it very efficiently. There's another procedure, which is the Metropolis-Hastings algorithm that I just explained. You can sort of make your test here that depends on all the n data points. You can make it stochastic as well, so you can develop. It only depends on a small number of data points. It's sort of an adaptive sequential test. I'll skip over it. There is still a quiz here, and I think that's important because we have 3 people still, or 4 people, I don't know, let's see if we can do these actually, since we skipped over a couple of stuff. So every MCMC transition kernel that leaves the target distribution invariant also satisfies detailed balance. That one we can do. Every MCMC transition kernel that leaves the target distribution invariant also satisfies detailed balance. And next one is by approximating the transition kernel, one can sample faster and reduce sampling variance, but may introduce asymptotic bias as a result. So this one I did talk about, but it may went a bit fast. So let's try this one first and see if we have a winner. So Everybody can, of course, participate, but I'm most interested in the 3 leftovers, or 4, I forget. So who thinks A is true here? Everybody. So that's it. Everybody now participates. Okay, a few people. Who thinks B is true? Or in other words, this thing is actually false. Okay. So it says every MCMC transition kernel that leaves the target distribution invariant also satisfies detailed balance. It's reversed, right? It's everything that, if you have detailed balance, you will actually satisfy invariance, but if you're invariant, you do not need to satisfy detailed balance. So B is true. So who of the people that, who still has everything correct? That's not very helpful. We still have 3 people. Okay, now we do this one then. By approximating the transition kernel, one can sample faster and reduce sampling variance, but may introduce asymptotic bias as a result. A, true. You're correlated. Okay, A is true, correct. So I think we have 3 winners. That's the. Okay, so this we covered. So some conclusions. So convnets express the right inductive bias for images, I think. So try not to ignore them. I think even for medical imaging domain, this is going to be important. Small data sets are challenging for deep learning in the medical domain, for sure. But there's also ways to improve the situation. We've looked at symmetries, we can do transfer learning, we can do semi-supervised learning, we can inject expert knowledge. Generative models are a really great way to express expert knowledge, let's say causal relationships or using a simulator. And so they can be much more data efficient. Okay, variational autoencoders combine the deep learning in the discriminative models with deep learning in generative models. And we can think of them as a sophisticated regularizer for the discriminative model, where you use actually sophisticated expert knowledge to regularize. Learning and inference in the presence of latent variables can be done with variational methods or sampling methods. So those are the 2 tools we talked about for doing inference and learning. And I think you cannot escape that these days, learning and inference methods really need to scale to large data sets. And we talked about the big data test and about, actually we didn't talk about it, but I think every method should also be able to be implemented in a distributed fashion. And I have references here for you to look at home. Thank you very much.